Good day, I am Angelica Marcos, and for this video, I will be presenting my output in modern geometry. Elliptic geometry studies the geometry of spherical surfaces, and in the said geometry, it possesses a characteristic postulate that any two lines in a plane met at an ordinary point. Best example of this is the longitude lines on the surface of the Earth, or as where we usually see in a globe. They may appear to be parallel at the equator, but the truth is they all met at both the north and south poles. Therefore, in this geometry, there are no parallel lines and no straight lines. Since the surface is a curve, therefore, lines drawn on this is a curve itself. So, in addition, the characteristic postulate of the elliptical geometry is satisfied by the four-line geometry. So, let's recall that four-line geometry is a finite geometry that consists of three axioms. The three axioms are, first, there exist exactly four lines. Second, any two distinct lines have exactly one point on both of them. And third, each point is on exactly two lines. Next, let's have Theorem 3.7.1. The segment joining the midpoint of the base and the summit of Sakiri quadrilateral is perpendicular to both the base and the summit. Let's have the figure Sakiri quadrilateral ABCD, and then let's recall the definition of Sakiri quadrilateral, wherein it has two right angles and two congruent sides. So for this figure, we have angle BAD and angle ABC as our two right angles. And then line AD and line BC are our two congruent sides. By assumption, E is the midpoint of the segment AB and F is the midpoint of the segment CD. Now we have AEB and CFD. By the definition of midpoint, we can say that line AE is congruent to line BE. Since the summit angles are congruent, angle ADC and angle BCD, then we can conclude that triangle DAE and triangle CBE are congruent by SAS postulate, or side angle side. Again, by the definition of midpoint, we can say that line DF is congruent to line CF. Of course, line EF is congruent to itself, and line DE is congruent to line CE by CP-CTC. So, by SSS postulate, we can conclude that triangle DFE is congruent to triangle CFE. By the definition of perpendicular, line EF is perpendicular to line segment AB and line segment CD. Therefore, we have proved that the segment joining the midpoints of the base and summit of a Sakiri quadrilateral, which is the line EF, is perpendicular to both. Next, let's proceed to Theorem 3.7.2. The summit angles of Sakiri quadrilateral are congruent and are obtuse. So, in this figure, let ABCD be a Sakiri quadrilateral with O and O' as the poles of the line segment EF. So, in Theorem 3.7.1, we have proved that line EF is perpendicular to both summit and base of Sakiri quadrilateral. And during our proving, we have found out that the summit angles are congruent because the two triangles are congruent. So, since our goal for this theorem 3.7.2 is to prove that the summit angles are congruent and are acute, and we have already proved that it is indeed congruent. Then let's proceed to prove that these angles are obtuse. So, to show that the summit angles are obtuse, it can first be established that their supplements are acute. Let's say, if X lies in BO prime and is the pole of the segment BC, then BX is greater than BO prime, and it is obvious based on our figure. Since BO prime is less than EO, therefore, angle BCD is obtuse. And earlier, we have proved that the two angle summit angles are congruent, and we have proved now that angle BCD is obtuse. Then automatically, angle ADC is also an obtuse. And at this point, we have proved the theorem 3.7.2, which is summit angles of Sakiri quadrilaterals are congruent and are obtuse. And now, we have theorem 9.20. In elliptic geometry, a Lambert quadrilateral has its fourth angle obtuse, and each side of this angle is shorter than the side opposite. So, let ABCD be a Lambert quadrilateral with a right angles at A, B, and D. Since the sum of the angles of any quadrilateral is more than 2 pi, then the angle at C must be obtuse. So, it is obvious in our figure. Let's then assume that one of the sides adjacent to the angle is greater than the opposite side. We then have BC is greater than AD. And then let E be on BC such that BE is equals to AD. Then we have angle ADE is equals to angle BED, since ADEB would be a Sakiri quadrilateral. However, angle ADE is less than a right angle, resulting in the sum of the angles of ADEB being less than 2 pi, and it is a contradiction. Next, assure that BC is equals to AD. Then, angle ABC is equals to angle BCD, and it is a right angle since ABCD would be again a Sakiri quadrilateral. However, we proved that angle BCD is obtuse. This second contradiction now allows us to conclude that BC is indeed less than AD. This means that a side adjacent to the obtuse angle is smaller than the side opposite. So therefore, we have proved the theorem 9.20. Next, we have theorem 9.21. The sum of the measures of the angles of any triangle is greater than pi. So let's have the figure. Let A, B, C be any triangle, and angle ABC and angle ACB be acute. So from A, let's draw AD that is perpendicular to BC. Then D must lie on the segment BC. And then the sum of angle ABC and angle BAD is greater than the right angle. And angle DAC plus angle ACD is greater than a right angle. So therefore, it follows that the sum of the angles of the triangle ABC is greater than pi. The amount by which the sum angles of any triangle exceeds pi, then it is called axis of the triangle. So by this, we have proved that the sum of the angle measurements of any triangle is greater than pi. Next, we have Theorem 9.22. The sum of the measures of the angles of any quadrilateral is greater than 2 pi. Okay, so let's have the figure. A, B, C, D is a quadrilateral. Since any quadrilateral can be divided into two triangles by either diagonal, just like in the figure, then this theorem follows readily from the previous theorem that we discussed. A quadrilateral can be divided into two triangles where, based on the theorem 9.21, that we have proved that the sum of the angles of any triangle is greater than pi. So, obviously, the sum of the angle measurement of two triangles is also greater than 2 pi. So, through this, we have proved the theorem 9.22 that the sum of the measures of the angles of any quadrilateral is greater than 2 pi. So, I hope everything is clear, and that would be all. Thank you.